Thank you, ladies and gentlemen. I will keep this fairly short, and it will not be technical. So, a change. I'd like to introduce Work Package 5. Work Package 5 is the first work package that tries to bring together all of the technical detail from Work Packages 2, 3 and 4 and package them in a way that can be useful for those responsible for making decisions at the building level, at the infrastructure level, at the regional level and at the national level. The aims are quite simple. It is to better understand the factors that affect vulnerability, resilience and adaptive capacity, and to investigate current models and current understanding to see which models are useful and which aren't. We're looking at the interrelationships, and I spoke this morning, I showed some of the models, so we're not just looking at individual measures, but at the relationships between measures. The context is liquefaction, but liquefaction is only one stressor. And one of the problems that comes out of the theory of disaster management and disaster resilience is the need to consider multiple stressors. And we've already had some introduction from Antonio that we need to think beyond the single first action to consequential actions. So the problem becomes a little more complex and a little more complicated. And so we're not going to do any fundamental new work in Work Package 5. We're going to work with our technical experts in Work Packages 3 and 4 to draw from them the knowledge that is needed for you to make decisions wherever you sit in that decision framework. So, we're going to develop a risk matrix. And the risk matrix, in very simple terms, has two axes. It has a vulnerability axis and it has a resilience axis. And what we need is to position buildings, groups of buildings, portfolios of buildings, infrastructures, people and society in these axes. Where do they sit? Are they highly vulnerable or do they have a low vulnerability? Do they have a high resilience or do they have a low resilience? Now the problem is very simple. No building owner, no municipality, no organisation is going to spend a lot of money investigating their risk unless they believe the risk exists. You cannot plan for what you don't know. So if you do not know you're at risk, you will not invest money. The problem is that in order to substantiate or establish that risk, our current tools are very complicated and very expensive. So you might know that your building sits in a potential liquefaction zone. But are the soils directly beneath the foundations of your building susceptible or not? Soil is not homogeneous. I'm not an engineer, but I listened to Misco this morning talking about different characteristics of soil. So you might have a map that has a 1 kilometre grid sensitivity. But in reality, does that reflect the soil beneath your building? We don't know. Are you going to invest in a full geological survey of the soil? No. Not unless you suspect a risk. Even if you have a risk, even if the soil is vulnerable, is your building resilient? What is its structural form? How does it respond? And again, you're not going to commission a full finite element analysis unless you believe there's a risk. So how do you know if you're there? How do you know if you're there? If you're there, or if you're there? And what we will do in Work Package 5 is a simple risk model. A risk model that doesn't require you to commission a consultant to make the first assessment of where you sit. I've already developed one of these in London, looking at climate change, looking at the vulnerability of buildings and infrastructure in London to flooding and overheating. So I have a framework, and we will use that framework, but we will change the stressor. The stressor will not be climate, the stressor will now be liquefaction. All right, so you know where you are. You sit in that high priority. You know you've got a problem, you know you've got poor resilience. So what are you going to do about it? What's your solution? So what's your mitigation? What techniques can you use? And again, you're not going to invest in a full structural design or a full geotechnic survey for ground stabilisation until you know the size of the risk. So can you improve your resilience but leave your vulnerability where it is? Should you improve your vulnerability but leave your resilience where it is? Or should you seek to do both? Each of those has costs. Which is the most cost effective? What are the cost benefits for the cost implications? And of course, you might be in a moderate zone and still looking to move forward. So the second part of the toolkit will allow you to make strategic business or investment decisions. Not detailed design calculations, not detailed costs at the design level, but strategic costs. Costs to the nearest €100,000. Because in the decision framework of many millions of euros, that is probably all you need at the early stages. Once you know you have a problem, once you know you have potential solutions, then you can invest in a detailed analysis and a detailed solution. So that's simple, yeah? Nice and straightforward. You can all go away and you can all work out what to do with your building, what to do with your infrastructure. No, there's a problem. I have described what happens for a building, or many buildings. I've talked a little bit about the infrastructure. But why would you improve the resilience of a building if it had no benefit for society? So what about business? A business may not be affected by a liquefaction event, but it could still be affected by the consequences of a liquefaction event. So if part of its supply chain is destroyed, that business will be affected. How do you cost that? How do you put the benefits in? What about households? They may not be affected directly by liquefaction, but if the business that employs the main earner in the household goes bankrupt, they have no money. So how does that affect their ability to function as part of a community? And of course, there are stakeholders that we don't yet know about. And so what we need to do is not just consider the building, not just consider the infrastructure, but to understand how changing the building or changing the infrastructure affects businesses, affects people, affects the community. And that's what the risk framework will do. We have a 10-step risk framework for flooding. I haven't shown it because it's too complicated and it's not relevant, but the principles are. So that's what we're trying to do. We're going to look at developing community performance measures. How do you measure everything I've just talked about without spending a fortune? How do you then integrate all of those relationships into a model? How do these metrics interrelate? Are they measuring the same thing or are they independent? If they are not independent, how do you deal with that complexity? Are you in fact dealing with a complex system, which engineers find really hard to evaluate? What are the cost benefits of doing an intervention? Why would you spend the money? And how then do you do this? Because you're not going to be able to apply these solutions simultaneously to all buildings. Buildings have a life cycle, 30 years, typically. So when in that 30 years do you intervene? And what's the cost benefit of not intervening early? How many lives are you prepared to risk by delaying an intervention? Hard fact, but it's something we have to consider because it's part of the cost-benefit analysis, the price of mortality and the price of morbidity. So we need to understand that. And then we're going to test it. So what are the metrics? We will have to define them. We will then have to develop a toolkit to collect them, and we will collect them hopefully in this region so that we can use you, we can use you as the test case. How do we do the cost benefit, and what's the framework? So that's what we're doing. That's how we fit into the main plan. That's where we are. We start in November and we finish in month 30. So thank you for your attention.